All right, let's get started. Before I get started, any questions from last classes? No questions? Yes, no? Hear you well. Am I audible?
Yes, sir.
Speakers are. All right. Okay, so if there are no questions, then we'll get started with today's lecture. So today we are going to get started with what we call as rigid body kinetics. So up till last class, what we were looking was at what we called kinematics, which means we were looking at what is the relationships or transformations between the different frames, and we were primarily interested in the NED, ECEF, and the body frame and the flow frame. How we interchange between these two, those are what we were looking at. So how does the kinematics change? How does the velocities or position vectors expressed in one frame can be related to position vectors and these ones in the other frame? Just give me a second here. Seems there's quite a loud noise outside. All right, much better. Okay, so today what we will be looking at is how to get to the equations of motion, and we will primarily be employing what is called as Newton-Euler formulation, which is nothing but essentially application of conservation of linear momentum and angular momentum. But before we get started, I want to introduce a slightly different convention for representing the vectors. So what we will do is we'll call them as coordinate free vectors, which means that we define these vectors without reference to a coordinate frame. Okay. So for example, let's say if I denote the vector V and B, then that is the velocity of the origin of the body fixed coordinate system with respect to the NED frame. But it is not expressed in any frame. I'm just referring to it as the vector. And if I specifically want to express it in some frame, then I'll write it as V and B, B. Then I am expressing this vector in the body fixed frame. Otherwise, I am just denoting it as a vector in a free space. So whatever frame I want to express it in, I'll express that as the superscript. So when I put n here, this means that I'm looking at that vector which is representing the velocity of the body fixed coordinates origin with respect to the NED frame, and that vector is expressed in n frame. Is the nomenclature making sense?
Yes, sir.
Okay, so similarly, if I have the position vector RBG, it represents the position vector to the center of gravity from the body fixed coordinates origin, and that's a coordinate free vector. But if I want to specifically specify, I want this expressed in the body frame, then this is how I will denote it. So that difference will be, we will try to make that into account, because it will help us out simplifying our notations a little bit. So rather than derive the equations of motion in a fully laid out manner, we can then use what is called as vectorial mechanics. So we can use vectors and we can describe how our mechanics is described in terms of vectors, and our equations of motion we can derive in the vectorial sense. So in order to achieve that, we will come with, we'll introduce this nomenclature of coordinate-free vectors. Okay, all right. So now when I want to look at the equations of motion about the center of gravity, it is generally pretty straightforward. It is rate of change of the linear momentum is the external force acting on the body. Similarly, the rate of change of the angular momentum is the external moment acting on the body. So that is what we are denoting here. Notice here that a couple of things I have to take care of. This is the derivative in a so-called I frame. I specify I as an inertial frame. Okay, so in an inertial frame, which is denoted by I, the derivative is given as d by dt, but a superscript of I on the right left hand side is provided. So in a we know that Newton's law are primarily applicable in an inertial frame. So in an inertial frame, I can write down the rate of change of the linear momentum, which is P, about the center of gravity is equal to the force that is applied at the center of gravity. Is this making sense so far? The first equation right here. All right. Notice here that momentum is nothing but mass times velocity. So in a sense, the PG vector, which is denoting the momentum, is the mass of the vehicle times the velocity vector of the center of gravity with respect to the I frame. And here we are using that notation of the free space vectors. Does that make sense? Yes. Okay. Same we are applying for the angular momentum as well. So rate of change of time of the angular momentum is the external moments acting about the center of gravity, about an axis passing through the center of gravity. Notice here though that this angular momentum is actually given by some inertia dyadic or inertia matrix times the angular velocity. And I have not really come about and defined this inertia matrix, and we are going to do that in just a little bit. So have some patience on what that inertia dyadic actually is. Those who have taken my course on maneuvering and control, you probably already have a sense of idea what that is, but those who have not, just please have a little bit patience. Okay, so notice that here I am talking about an inertial frame. So what should be our inertial frame? Should it be N? Should it be E? Might be a question which might pop up. But most of the marine craft applications that we are interested in, we can assume that the NED frame to be an inertial frame. So in which case, we will just change this subscript I to N when we are denoting these application of Newton's law in the NED frame. We can get away with it because the forces on the marine craft due to the Earth's rotation are quite small compared to the hydrodynamic forces that the craft experiences. Since these forces due to the Earth's rotation are really small compared to the hydrodynamic forces, the effect on the dynamics is also equally small. The only exception where we might want to not disregard the idea that NED is a inertial frame or not consider that NED is an inertial frame is when we have ships which are stranded at sea and they are drifting over large distances. In that cases, it possibly is that we may not be able to make this assumption that the NED frame is a non-inertial frame, is an inertial frame. But for most practical applications, we should be able to make that assumption. So our inertial frame for most applications will be equal to the NED frame. Is that making sense for everyone? Yes, sir. All right. Okay. Note that, so therefore, since our inertial frame is the NED frame, we can represent those free vectors which we were denoting as the velocity of the center of gravity in the inertial frame as velocity of the center of gravity with respect to the NED frame's origin. Similarly, the angular velocity omega ig is given as omega ib. Okay. Notice here that there is a change. What's happening here? The angular velocity of the body about a axis passing through the center of gravity is equal to the angular velocity of the body passing through an axis about the center of or the origin of the BCS. Is this making sense? Why these two are equal?
Sir, what omega AB represents what? Okay.
Okay, come again, Joel. I couldn't hear.
Omega AB represents angular momentum with respect to, and what is introduction?
Yes, this is about an axis passing through the origin of the body coordinate system. Whereas this represents an angular velocity of the body about an axis passing through the center of gravity. And they both will be equal because the angular velocity cannot change in a three-dimensional Euclidean space, right? Whether it is rotating about any axis, no matter where I put my coordinate system, the angular velocity of the body remains the same.
Yes.
Okay. So that is why you will see that the angular velocity of the body with respect to an inertial frame, with respect to either CG or the origin of the body coordinate system is equal, which in this case is nothing but I is nothing but n, so I can represent that as omega nb. So that is telling me what is the angular velocity of the body about an axis passing through the body coordinate system's origin with respect to the NED frame, because NED frame is our inertial frame. Everybody with me so far on this?
Yes.
Fantastic. Okay, now we have to introduce something of a notation, the time differentiation of a vector A in a rotating frame B. Note that our B is our body fixed frame. If you want to express in that frame, the time derivative is not the same as what you would expect in a inertial frame. Because the body coordinate system is non-inertial frame, you'll have some extra terms creep in. And the relationship between them is given by the time derivative of a vector in the inertial frame is equal to the time derivative of the vector with respect to the body fixed frame plus the omega ib, which is the angular velocity of the body cross the vector A. Now, I'm not going to be going ahead and proving this result explicitly, but we can try to take an example in order to see how this works. So let me try to put it here. All right. So the contention is d by dt with respect to an inertial frame of a vector A is equal to d by dt with respect to a body fixed frame of the same vector plus omega I b cross A. For example, let's take a simplistic case. Let's consider that we are looking at an inertial frame as shown here. Okay. Let's say, okay, and I'll say x, y, and z. Okay. Just do this one. Okay, this is xi, yi, and zi. Let's say the body fixed frame at that instant is looking somewhat like this. And that I'll call as xb, yb, and zb. To make things simpler, we can try to consider things in a what you call 2D plane, and that is the example which we will look at. So let this be the vector. Now this is applicable in the most generic case in a 3D case, but the example which we will try to look at we'll try to restrict to a 2D case so that we can possibly manage it within our time frame. But the same concepts apply to the 3D case as well. Okay, so let's say I have xi, yi. So zi will be pointing which way?
Out of the screen.
It will be pointing out of the screen, right? Correct. And then suppose, let's say that my xb is looking something like this, and then yb is looking something like this. Let's see. Okay. Now let's say that my original a vector which I had is not a time varying vector, and let's say that that vector has a components 1, 0, 0 in the inertial frame. Okay. Now assuming that this body coordinate frame is rotated by an angle psi, okay, can you tell me what is the position vector of this vector A in the body fixed frame? What is the position vector of this vector A when I express it in body fixed frame? So in essence, if I wanted to write this properly, this would be representing A vector in I frame is 1, 0, 0. I want to find out what is that A vector in B frame. What will that be?
Cos psi minus sin psi 0
Cosine of psi
minus sin of psi
sine
comma
of
0.
psi, comma 0. Is everybody able to see this? Everybody clear with this?
Yes, sir.
Yes, sir.
All right. Now let's assume that this angle psi is actually nothing but some omega times t, which means that the body fixed frame is actually rotating with respect to the inertial frame by an angular speed omega. Okay, and at any particular time instant I have considered this. So in which case I can write that the same vector which is not time varying in the inertial frame has a time varying nature in the body fixed frame. And what would that be? Is that making sense?
Yes, sir.
Okay. Now I want to take the derivative of this vector A with respect to the inertial frame. Okay. So I know that I want to take the d by dt of I of A vector. What would that be? When I take the derivative in the inertial frame?
Zero.
0, right? Because it's not varying. It's a fixed vector. Its length doesn't vary in the inertial frame. Is everybody with me so far?
Yes, sir.
Okay. Now we'll try to compute the same thing from the right hand side of this equation and see whether we are matching up with it or not. First, we'll calculate this term, d by dt of A in the body fixed frame. So when I take d by dt in the body fixed frame of the same vector, what do I get?
Omega sin omega t minus omega sin omega.
Correct. Minus omega sine omega t, comma
Minus omega cos omega t.
minus omega cos omega t,
0.
and then 0. This is what we get. Now let's try to understand what I get if I take the angular velocity of the body cross the vector A. All right. So now I want to find out what is my angular velocity of the body. How is the angular velocity of the body denoted? In this case, what will the angular velocity of the body be, assuming that this is rotating by some value omega?
0, 0 omega.
0, 0 omega, right? So that will be what will be my angular velocity, 0, 0 omega. All right, and now I want to take a cross product of that with this one. So I want to take omega IB cross product of that with the A vector, which means I simply have I, J, K, and then I have 0, 0, omega, and the A vector will be in cos of omega t minus sine of omega t, 0. This row here. What do I get when I solve this? What do I get for I?
Minus omega sin omega t.
Minus or plus?
Plus omega.
It's just
plus
omega.
sin omega t.
It's omega sin omega t. Then what is the y component?
Omega cos omega t.
Something went wrong, isn't it?
Minus omega.
Yeah, it will be minus omega.
Cos omega t.
No, it will be
It will be omega cos
Plus
omega t.
cos omega t.
Minus j.
omega cos omega t.
Answer.
0, right? Now, if I add this and this together, what do I get?
Zero.
I get 0, right? So this is indicating that if I take the derivative in the body fixed frame and add it to omega IB cross A in the body fixed frame, I should get the same derivative as what I get in the inertial frame. Now this is not a real proof because I have really considered only an example and I'm showing you that it happens like this, but it can be argued that this same thing occurs and the formula is valid even for a three-dimensional rotation, a generic three-dimensional rotation. Okay. All right. So what we have is that the time derivation of a vector A in a rotating frame satisfies this equation which we just saw, and we actually looked at an example where this is getting satisfied. We will denote the differentiation in the body fixed frame as dot. So if I write any vector dot, that means that I'm actually taking a time derivative of the vector with respect to the body fixed frame. That will be our nomenclature that we will use so far. If I'm taking a derivative with respect to the inertial frame, I'll typically try to write out this entire expression d by dt with a superscript I to denote that it is being considered in the inertial frame. Is that making sense?
Yes, sir.
Yes, sir.
Okay. Now we are in a position to start looking at the translational motion of the center of gravity. All right. So we know that the location of the center of gravity with respect to the NED frame is R and G, and that can be taken to be equal to RNB plus RBG. So let's try to see what I mean by that. So I have the NED frame here. So this is I or N, which is nothing but the NED frame in our case. And from that origin to the center of gravity, so this is the center of gravity G, and this is the center of origin O. So what I'm saying is R and G, this vector here, is equal to R and B plus RBG. Is that making sense?
Yes, sir.
Yes.
Alright. Now, if I take a derivative of this expression with respect to d by dt in the NED frame, then I'll get the velocity of the center of gravity with respect to n is equal to velocity of this body coordinate system's origin with respect to n, and then I have this derivative of b to g. Yes?
Yes, sir.
All right. Now this derivative with respect to RBG, okay, with respect to the coordinate system frame n, can be expressed in the body fixed frame as d by dt b of RBG plus omega nb cross RBG. Just using the above formulation which we had just figured out, because we are converting from the inertial frame into a body fixed frame derivative.
Yes, sir.
All right. Now we know that in the body fixed frame, the position vector r, b to g really does not change, right? Because no matter how the ship will rotate out, the r, b to g will always be not changing with time, because with respect to the body fixed frame, because as the body moves, the body fixed frame also moves with it, so the relative location of g with respect to O does not change. Is that making sense?
Yeah.
So that is why this derivative of RBG with respect to the body fixed frame derivative will be 0. So this term right here is becoming 0. So that means our velocity of the center of gravity with respect to the NED frame is equal to the velocity of the body coordinate system's origin with respect to NED frame plus omega cross RBG. Everybody with me so far?
Yes.
All others too?
Yes, sir.
Okay, fantastic. Alright, now we are in a position to apply the so-called Newton's law. Remember, our Newton's law was that the force acting at the center of gravity will be equal to the time derivative of the linear momentum, which is mass times velocity. And velocity here represents v and g. Velocity of the center of gravity with respect to the NED frame. And I'm taking a derivative with respect to the NED frame. I can express this derivative in terms of the body fixed frame as we just saw before. So in that case, I have an additional term which comes in, which is omega nb cross v and g. Up
So
till
this
here,
will be P and B, right?
sorry,
Uh, in the second part of the equation, like should be M B and B plus M omega and B plus M.
m is a scalar quantity here, right?
Okay. Oh yeah, yeah. Okay.
I can just take it
That's
out. Right? Because it's a scalar, I can take it out. That's
yeah.
it. Can't do the same with inertia, and you'll see that in that case I have to actually maintain the order of multiplication. But for this case, since it's m is scalar, I can take it out. So I can express this derivative. Since the mass is not changing with time, I can pull mass out. So therefore the external force is equal to mass times v and g dot, which is the derivative of the velocity of the center of gravity with respect to NED frame, plus the omega cross v and g. Okay, same thing, I'm just taking mass as a common factor here. Now I can express this thing which I have expressed in a vector form. So this is expressed in a vector form. I can express it in a matrix form as shown here. Tell me if this is convincing enough.
Okay.
What do you guys think? Everything okay with it? Yes, no?
Yes, sir. All these all the quantities in the curly braces are vectors, right? 3 cross 1 vector.
Correct. So these are 3 cross 1 vectors.
Yeah.
Right? But now only thing, the difference you'll observe that now I'm expressing them in the body fixed frame. Okay? These quantities are expressed in the body fixed frame. In fact, there should be a P here as well. Okay, those vectors. So whenever I want to convert this coordinate free vectors into a matrix form, I need to choose one frame in which I express these vectors. So here I'm choosing the body fixed frame and I'm expressing those vectors in it.
So how did means the right hand side FG, how that came in the body fixed frame?
That is the force vector, right? External force acting on the body.
Okay.
Okay?
Yeah.
I'm just expressing all the vectors in some frame. In a coordinate free vector, I need not express it in any frame. That was what the nomenclature we went ahead
Okay.
with.
Yeah,
Right?
yeah. Yes.
Here we are putting them all in one frame.
Yes.
Only thing I have to be consistent, right hand side and left hand side should be in the same frame of reference. I should not mess up there. Okay, is everybody with me here? Especially this portion, is it clear for everybody? We have seen this before, that the cross product can be expressed as a skew symmetric matrix due to the first one times the second vector. We can express that cross product as a matrix multiplication operation.
Sir, I have a doubt.
Yes.
Sir, if this has to be represented in matrix form, is it necessary that it should have some frame of reference? Like,
Yes. Whenever we want to express it in a matrix form, we typically would like to know it in a frame of reference. It has to be in a consistent frame of reference.
yes, sir.
Okay, all right. Okay, now let's try to look at what happens with the rotational motion about the center of gravity. So far what we saw here was the translational motion of the center of gravity. Let's try to understand what is happening with the rotational motion. We follow the same approach. The external moments acting about the center of gravity is equal to the d by dt of the angular momentum. The only difference here is that this angular momentum is an inertia dyadic times the angular velocity. So whereas mass was scalar, this thing is not scalar. This thing is a 3 cross 3 matrix. We will define the terms in this matrix in just a little bit, so have a little bit more patience. We'll especially see what are the terms in these matrices. But please understand that this is simply a counterpart of what you saw as mass times velocity being linear momentum. It is inertia times the angular velocity, which is the angular momentum. Okay, notice that omega ng, which is the angular velocity with respect to the center of gravity, is the same as angular velocity with respect to an axis passing through O. So therefore, we can represent this as omega nb. Now, this time derivative is with respect to an inertial frame. That is where the Newton's laws are valid. But if I want to convert that into body fixed frame, I can express it as the derivative with respect to the body fixed frame. But then I have to add an additional term, which is omega nb cross ig times omega nb. And notice here that I could not take ig common, like how I did for the mass. Here I could take mass out common because it's a scalar value. I could not do it here because this is no longer a scalar. Is this making sense so far? The only thing I'm doing here is taking the fact that the inertia matrix is not time dependent, so I can bring it out. So the derivative only applies to the omega nb. So I'm taking the derivative of omega nb minus this term. You only see that here I have changed the order of cross product, so that is why this minus sign is coming. Up till here, everybody with me? All right, in the matrix form, so this is also in the vector form. If I wanted to write down this equation in the matrix form, then I would go ahead and say that I'm taking the inertia matrix about the center of gravity in the body fixed frame times the omega nb dot in the body fixed frame minus I'm going to construct a skew symmetric matrix obtained after the multiplication of Ig and omega nb. Then that I'm going to pre-multiply with omega nb, and that should be equal to mg. Same concept as before. We are taking this coordinate free vector form and expressing it in a body fixed frame in the matrix form. That is why you will see superscripts here. There were no superscripts here. Okay, all right. Now let's talk about this inertia matrix before we go any further. This inertia dyadic basically is a 3 cross 3 matrix, and it is defined as it has 6 unique terms, and this inertia matrix will always be symmetric, which means that if I take IGB, it is equal to IGB transpose. Okay, it's always symmetric. And the terms in each of these, I'm going to define, those are nothing but the moments of inertia. Especially along the diagonal, we'll have what are called as moments of inertia, where we are considering a volume integral of across the entire body, and then we are computing what is the contribution due to each small portion of mass in the body about the x-axis. So which means we are looking at what is the distance from the x-axis, which is why we have y square plus z square. First term. Is this making sense?
Yes, sir.
Okay. Similarly, the other two terms also, where I'm looking at the distance from the y-axis, distance from the z-axis. So that's why you have x square plus z square in this case, x square plus y square in this case. These three terms are known as second moments of inertia, or mass moments of inertia for the vessel. Now, all the other terms, you'll see that because of the symmetry of this matrix, Ixy must equal to Iyx, Ixz must equal to Izx, and Iyz must equal to Izy. Now, we'll define those three other terms, and these terms are called products of inertia, where we are kind of considering x times y times rho m times dv. So what is a small unit elemental mass in the body? How far is it located from two different orthogonal planes? So x here denotes the distance from the yz plane, and y here denotes the distance from the xz plane. And similarly, we have the other products of inertia also defined. This is the counterpart for when you are looking at what is the angular momentum of the body. It can be expressed as this inertia matrix times the omega, where omega is the angular velocity of the body. All right. So if I combine everything together now, I can express my complete equation of motion in this form. Notice that if I go back here, just to see whether we have the right thing or not, I have m times vng dot plus s of omega nb times vng is equal to fgb. Okay, so that, let us see whether we are getting the same translational equation of motion here. I have mass times vng dot plus ms omega nb times vng is equal to fg. That is what I get on the first row after multiplication. Is that making sense?
Yes.
Yes, sir.
All right. Now let's look at the second row. I have Ig times omega NB dot minus S of Ig times omega NB multiplied by omega NB is equal to mg. Let us see whether that is what we had here. That is exactly what we had here. Ig times omega NB dot minus S of Ig times omega NB multiplied by omega NB is mg. So I'm basically expressing the two equations which we derived, two vectorial equations together which I derived in a full matrix form, and I'm calling this matrix which you see here, that matrix as MRP, and this matrix here as CRB. So in that case, I can write this down as MRB about the center of gravity times the derivative of the linear and angular velocities plus CRB about the center of gravity times the velocity, linear and angular velocity, is equal to the force and the moment. Is this making sense? Yes? Yes or no? If it is no, tell me. We'll go back and look at it again.
It is clear, sir.
Sorry, couldn't hear you.
It is clear, sir.
It is clear for everybody? Others too?
Yes, sir.
So the last part, like we changed the matrices and named them these things, right?
Yeah. So we just named these matrices MRB and CRB, that's all. It is the same equations. We didn't even do any manipulation here. It's exactly the same equations. Ig times omega NB dot minus S of Ig times omega NB multiplied by omega NB is mg.
Yes.
So no manipulation. We just express them in the matrix form. That's all.
Yes, sir.
All right. Now, although this is convenient in the center of gravity's frame, so here notice that all the quantities are expressed about the center of gravity. We are looking at what are the forces acting at the center of gravity. We are looking at what is the velocities of the center of gravity, but it's not always clear that we want to express this in this form because the center of gravity may change. As we had discussed previously, on an onward journey, the center of gravity may be at a different point, but in a ballasted condition when the vessel comes back, the center of gravity may be at a different point. So each time, since the center of gravity and the quantities with respect to that, the mass and other things are going to undergo a change, it makes much more sense to express these equations about the body fixed coordinates origin, or the so-called coordinate origin. So now what we will do is that these equations which we derive about the center of gravity, we want to convert them or transform them into about the coordinate origin CO. Is everybody with me what our plan of action is?
Yes, sir.
Yes, sir.
Alright. So let's go further and see what we do. Okay, so here is where we will start to use a little bit of linear algebra in order to help us with some of the mathematics. So pay a little closer attention. It might be worth to take a look at it. Notice that we already saw that the velocity of the center of gravity with respect to n is the velocity of the body fixed coordinates origin plus omega cross rbg. We saw this relationship previously. Only thing here I have done is I have expressed it in terms of body fixed frame instead of the free vector space. We saw this before. Everybody with me so far?
Yes, sir.
All right. Now all I'm doing here is I'm going to convert this second cross product. I'm going to interchange the cross product. So therefore I need a minus sign. So I have minus RBG cross omega NB. And the reason why I want to do that is then I can express this in a matrix form. So V and G can now be written as V and B plus S of RBG transpose times omega NB. Is this making sense? If it was only this cross product, I would have had S of RBG times omega NB. But since I have a negative value, I can take the negative value into the skew symmetric matrix, and we know the property of skew symmetric matrix that minus S of RBGB is nothing but S of RBGB transpose. That is the definition of a skew symmetric matrix, isn't it?
Yes, sir.
So therefore I can write this expression as in this manner, which you have seen before here. Okay, so with that in hand, I can convert the so-called velocity vector, general velocity vector, which I had in the equations of motion about CG, where I was looking at the velocity of the center of gravity and the angular velocity of the body. I can express that as some matrix times these quantities, where this is the velocity of the body fixed origin and this is the same angular velocity as before. Is this making sense?
Yes, sir.
So the same equation which I have above here, I'm expressing that in this form where I'm putting a matrix times the new velocities. The only difference is instead of the velocity about the center of gravity, I'm changing that to the velocity about the body fixed origin O. Alright, this matrix is what I will call as the H matrix for my purposes. Notice that if I take a transpose of this H matrix, I get this value here. Zoom out a little bit. All right. So when I take a transpose of this matrix, the identity remains as the identity matrix remains as the identity. This quantity here will come over to the other side, but then the transpose is lost.
Yes, sir.
Is everybody with me so far? This should be pretty straightforward. This is simple mathematics or linear algebra. Now, the reason why I want this transpose here is what I'm going to do now is go back to our equations of motion about the center of gravity that we derived, and I'm going to pre-multiply it by this on both sides. I'm going to pre-multiply it by this transpose matrix on both sides. So then what happens, this is what I end up with. So I pre-multiply with the transpose here, here, and here. And then the velocity vector, which was about the center of gravity, I also express that about the body fixed frame using the expression which we just derived here. Okay, so therefore instead of V and G, we have V and B, but then we have the H matrix in front of it. So that is why we have H transpose M times H multiplied by the velocity vector, where everything is in the about the body fixed origin. And similarly, we have a transformed C matrix, which is H transpose CRB times H. Is this making sense?
Yes, sir.
Yes, sir.
All right. So now, if I were to look at what this new mass matrix of mass, the rigid body mass matrix and the Coriolis matrix CRB are, if I expand these multiplications out and see what happens, this is what I'll end up with. I'll end up with the mass matrix having the mass times the identity matrix minus m times the skew symmetric matrix with respect to where the center of gravity is located with respect to body fixed origin. And this one will be the same, but no minus sign here. And finally, we'll have the inertia matrix minus m times s square of RBG. Okay, that is simply coming about by doing this multiplication. So I take this H transpose, multiply it by my previous mass matrix, and post multiply it by H. This is what I should get. This can be verified actually, that this is what you will get. Similarly, I can show that the Coriolis matrix is given by this expression, which we see here. Is this making sense?
Yes, sir.
Yes. Okay, fantastic. So now I'm going to stop right here, because then we will next time, once we have these matrices, we'll discuss about how the translational motion about the center of, about the coordinate origin and the rotational motion about the coordinate origin look like by putting these mass matrices and the new velocity vector into it. What do we get? That is what we are going to take a look in the coming lecture. Okay, I'm going to upload these notes up today. Please feel free to take a look. Sometimes these can be looking to be very clear when we are actually just going through the derivation, but it makes much more sense when you actually want to derive it yourself and convince yourself that you have fully understood it. I would encourage you to do that. Spend some time to see if you're able to follow the steps along by actually writing it out on a piece of paper. So then this will be crystal clear in your head. This will be important because many a times the equations of motion are the starting point for control or navigation, and one has to have a firm grip on them in order to appreciate what is going on next. Okay. So please take a look today. I'll put them up, and you can take a look and try to figure out whether you have understood it fully or not. If you have any more questions, feel free to buzz me. On Monday, we'll continue back with this. Any questions so far?
Sir, first we expressed all this equation, this MRB into V dot plus CRB into V. That was expressed in about the center of gravity, right?
Correct. That was expressed in the center of gravity. That is why you have seen this subscript of CG.
Yeah, that's what I didn't understand. How is it about the center of gravity? Because of this.
No, I am deriving the equations of motion first about the center of gravity. Then I want to transform them into equations of motion about the other coordinate frame. Which is why when we had the mass matrix with respect to the center of gravity, you will see that there are nothing happening here. These are zero.
Okay.
Right? Whereas when we have the non-center of gravity as the location, you will see that that has the dependence on the position of where the center of gravity is with respect to the new origin.
Okay.
And what you see here is actually nothing but the so-called parallel axis theorem.
Yeah, but there is ideally it should have been plus, right? No. Yeah. Okay.
No, this is because if you look at it, it will be IGB
Yes.
minus R cross omega. Right? If if I multiply by omega dot, sorry. You are thinking why it is not plus m
Yeah.
square, right?
Yes.
M square omega.
Yes.
That is in the scalar case, but here it is in the vector form. So these are vector cross products. That is why you see the difference. But if you interchange the order, you will see that the minus sign disappears here.
Okay.
Okay. In fact, if you turn off and you try to figure out what is the value, or in a 2D case, you will actually find that it will come up to be this. So if you multiply these two matrices together, okay,
Yeah.
and assume that all the action is happening about only 2D space, okay, which means the rotation is happening about only one axis.
Yes.
Then you can convince yourself and see whether you are getting this value or not. You should get this value.
Okay.
Okay. We'll
Yes.
talk about this parallel axis theorem tomorrow on Monday when we talk. We'll discuss about this a little bit. All right. Any
Yes.
other queries? No other queries. I'll stop recording now.